So in this video, I want to talk a little bit about changing an object's angular momentum. And to think through that, I want to start with part 3 of the rotational collisions lab you did. So I had you graph the final angular velocity of the block on the vertical, and I had you plot the distance from the center of the block that the marble hit on the horizontal axis. Now, you should have gotten a nice straight line for this. And it is worth noting that for the distance, it didn't matter whether that distance was above the center of mass of the block or below the center of mass of the block. It just mattered how far from the center of mass. Now, we were using these quantities ultimately as a stand-in for something else. Now, the block has the same mass, it's got the same distribution of mass in every single impact, and so its rotational inertia was the same in every single impact. And so if we had multiplied the final angular velocity by the block's rotational inertia, we could have instead plotted the block's angular momentum after the collision on the vertical axis. Now, another important assumption that we're making is that these impacts lasted had the same force every single time. And so every time that marble hit the block, it hit with the same number of newtons. Now, if we do force times the distance from the center of mass, we get torque. So what we're seeing is that there's a linear relationship in this case between the angular momentum and the torque. So the more torque you apply, the more angular momentum that block gained. Now, something this doesn't account for, all of these impacts took about the same amount of time. But if you apply the torque for a longer amount of time, you should get a larger change in angular momentum. If you give something a very, very short torque, so you push it or pull it for a very short amount of time, it's only going to speed up a little bit. If you push it or pull it for an extended amount of time, it's going to speed up a lot more. So that leads us into this equation right here, which is on your formula sheet, where the change in angular momentum equals torque times the time that torque is applied over. And this is sometimes referred to as angular impulse. Earlier this year, we talked about impulse for linear motion, where impulse was the change in momentum. Now we've got angular impulse, which is the change in angular momentum. So again, we're seeing these real strong parallels between what we already learned about linear motion and what we are learning now about angular motion. In fact, this is one of the reasons why I like to do angular motion and rotation last, is we're essentially able to build in some review of important concepts from earlier in the year. Now, we were able to use this impulse equation with SOS diagrams earlier this year, where if you had some impulse, then with the interaction diagram, you would do the force times the time that impulse was applied over and add that to your initial momentum or subtract it depending on the direction. Now, we also ended up using some graphs. Now, we figured out if you do a force versus time graph, if you have a constant force, and I should label my axes, so if you have a constant force on a force versus time graph, that area is force times time. And so the area of a force-time graph is going to be the change in momentum. And then we were able to use that to deal with situations where we don't have a constant force. This formula we have assumes the force is constant, But if we have some situation where the force is increasing or decreasing or otherwise changing, we can still sketch that graph. And as long as you can find the area of this graph, so for example, if you did the area of this triangle instead of just doing force times time, you would get the change in momentum. It turns out something very, very similar works for angular momentum because we have this really similar equation. Instead of change in linear momentum equals force times time, we now have change in angular momentum equals torque times time, because torque plays a very, very similar role to angular motion as force does for linear motion. And so if I make a graph of torque versus time, and I find the area of that graph, that area will be the change in angular momentum. And we can again get to that idea from the equation, because if we had a constant torque, the area of that graph would just be torque times time. Now, with linear momentum, we also did some rearranging this equation to get to delta P over delta T equals force, which told us that if instead of doing a force time graph, if we did a momentum time graph, then the rise on this graph would be delta P, and the run on this graph would be the time. And so we were able to figure out that the slope of a momentum time graph equals force. We can do something very, very similar with angular momentum. So now instead of momentum over time, I'm going to have angular momentum over time equals torque. So if I have angular momentum on the vertical and time on the horizontal, then the rise of this graph is the change in angular momentum, delta L. The run on this graph is the time, delta T. And so the slope is going to be delta L over delta T, which is torque, or the Greek letter tau. So we're seeing that these graph relationships that we learned for linear momentum work in some very, very similar ways for angular momentum. And so we're going to end up being able to use this equation to solve problems in a very, very similar way to how we did with this equation for linear momentum.